Thank you. I will repeat. My name is Ismael Solis. I am a data scientist and performance analyst for the Spectrum Scale project at IBM. Probably you already know Spectrum Scale. Spectrum Scale is our software-defined storage solution. Software-defined storage solution, and my work there basically is analyze a bunch of data related to performance in order to maintain the quality of this particular software component, but also is to work closely with customers, support services, and also with development teams in order to investigate which are the best tuning profiles for particular scenarios where this software-defined solution is going to run. And this, if you have been involved in such activities, is not a trivial task because, as the guys in the previous presentation have mentioned, the performance can be affected by many different parameters. So it involves a lot of experimentation, a lot of testing at different levels, by at the end coming with a tuning configuration profile that will help to obtain the maximum performance, or at least an expected performance by customers. Okay, this presentation is not related, as others have been given during this conference, to a particular hardware advance in storage, or an architecture, or a protocol for storage. This presentation is related to an effort that we are doing at IBM for constructing a data-driven platform in order to exploit the performance data that we are continuously collecting, and how we're using this data in order to do some smarter things using machine learning APIs in order to classify and also to recover tuning profiles that can help performance analysts, performance engineers, data center system administrators to close the gap between the configuration that they have physically with the performance or the tuning configuration that they need to use for that particular environment with specific characteristics. During this presentation, I will discuss the challenge of tuning performance for software-defined storage solutions. I will introduce the data-driven performance platform, basically what we are doing in order to collect all the data and start just processing it to do analytics and also machine learning treatment of this data. Particularly, I will focus on this machine learning-based configuration profile repository. That is the one that I want to show off today, in which we are deploying all these tuning configuration profiles, and how we are classifying and recovering these configuration profiles or tuning profiles from this repository. Finally, and hopefully, we will have time for comments and questions. I think for us, your feedback is very important. I have to be clear. This approach is in very initial steps. We are working hard to close all the gaps that we have in the implementation at this moment. But of course, if you have any idea, any comments, or feedback about how we can improve it, it is welcome. Okay, so the first thing that we have to do is to stay clear what is a software-defined storage solution. Well, software-defined storage solution is not more like a piece of software that we put on top of a bunch of hardware, and would help us to decouple, to abstract all the complexity of that hardware to make our storage resources more flexible, more available, and increase in some way the performance. Okay, this approach is enabling the storage resources to be an integral part of a larger architecture that could be the data center software-defined architecture. Okay, and here with that, what we are looking is that we can easily automate and orchestrate the use or utilization of such resources. So basically, what we are looking with the software-defined storage solution is a set of functionality that include blocks, file, object store, and obtained some benefits such as flexibility, scalability, low cost, and basically abstract the characteristics of any hardware to deploy our solution. So that's software-defined storage. Okay. So when administrated correctly, and I have to correct this, when administrated and configured correctly, software-defined storage is going to increase the performance, availability, and efficiency. That's clear. Okay, but administrating software-defined storage and configuring it is not that simple. Although we have mentioned that software-defined storage is going to abstract all the hardware complexity, this is only for the end users of this type of solutions. However, for the system administrators, the data center engineers, it's still a very complex situation because they have to deal with very complex environments, okay? We have large number of nodes, from tens to hundreds of nodes that are deployed in large data centers, where we have hardware heterogeneity, different architectures with different characteristics, with different capacities that we have to deal with. We have diverse and complex workloads. The presentation before, they just talk about how complex it is to measure and how complex it is to evaluate the characteristics of the workload. Well, in real environments, we have diverse and very complex workloads that, of course, affect the performance of the overall solution. And on top of that, well, we have the intricate network characteristics. We have InfiniBand, we have Ethernet, we have fiber and fabrics, etc. So it is a very, very complex environment that we have to deal with as system administrators, as data center engineers. So the question here is, how should I configure my software-defined solution considering all these characteristics to get the best performance, availability, and efficiency? Well, the answer for that is very simple, okay? But this simplicity comes with very complex activities. It's very simple because the answer is it depends, okay? It depends about the characteristics of everything that we have mentioned before. And it involves a lot of testing, yeah? A lot of experimentation in order to tune the software-defined solution based on the characteristics of our environment. So intrinsically, the software-defined solutions are very flexible. That means that they are hardly customizable, okay? So we can change many things. So that means that they have several parameters that can be adjusted. And we say several, they are several, about 100 parameters that you can tune in order to start thinking about how to use properly your software-defined storage solution to maximize your performance, availability, flexibility, etc. Okay, so even when you have identified a subset of these parameters, for example, reduce it to a couple of tens parameters, sorry, the combination of these parameters with the possible values that they can have is still very big. So it's still a very complex situation to tune the configuration. So what we are doing in order to determine the best configuration or the best tuning configurations, well, the first thing is we are relying on general application best practices. We have documentation that you can find online, and you see some best practices based on some general characteristics of environments, some ideal situations where you will find some parameter values or some recommendations that most of the time you have to make an interpretation of how to take this best practice to your real environment, okay? And on top of these best practices, we have highly skilled engineers. These highly skilled engineers are traveling all around the world, meeting with the customers, sitting inside of the labs or inside of the data centers and working beside with the data center administrators and data center engineers to making all these tests, to gathering all this information, all this data, and then finally come with a complex tuning configuration. That could be probably 1 or 2 tuning parameters that could be required in comparison to the default values. But finding these values for these 1 or 2 parameters is extremely complex. So basically, we are relying in these 2 major approaches. So what are the problems with these 2 approaches? Well, the first, best practices are always a very good start point, I consider. You are not starting from scratch. At least you have an idea and what you can start looking at and what to tune in the configuration of the software-defined solution. But best practices do normally not cover all the possible scenarios. I mean, when we are in real scenarios, we have a lot of complexity, as we have mentioned, and normally best practices don't fit directly, and you have to do a very good estimation on how to apply this best practice to this particular scenario. And best practices get deprecated with the time. Even if you don't modify the software, if you start modifying or doing rotation of your hardware, the best practices start getting deprecated. On the other hand, the knowledge that is acquired by human experts can be highly diminished by the rotation of personnel. This is very normal in every company, in every enterprise. So the lack of expertise and skill sharing is also another problem. So these kind of persons are always traveling, having a lot of meetings. Normally they don't have too much time for these activities of sharing the expertise and skills. And it becomes very difficult for other engineers, for other performance engineers to start considering the expertise or to start having in mind the expertise that another engineer in the other side of the world is using to solve particular problems. So here is where we think that there is the need for a knowledge repository and a computing artifact or module to smartly classify and recover the tuning profiles. Okay? So basically what we are saying is where instead of letting all this knowledge in hands of the engineers, let's take all the data that they are collecting, because all these engineers are already collecting the data. Let's put all this data into a repository, and from there we are going to derive the tuning profiles, and we are going to store them in a repository that then will be available for other engineers just describing in natural language the characteristics of a new environment. So for doing that, first, we are setting up a data-driven performance platform. Basically, this data-driven performance platform, what it looks for is to be a place where we can start just collecting all this performance data that we are generating from our labs, that we are generating from proof of concepts, what we are generating from the experimentation that sometimes we run with our customers when we are deploying particular scenarios with very particular characteristics. So the objective for this data-driven performance platform is to develop a scalable platform to efficiently process, store, query, and analyze the data from the performance evaluation of different solutions that we are deploying. What we are looking as characteristics of this particular platform is to provide mechanisms to ETL all the data that we are collecting. We are collecting data not only from the benchmark results, okay, that could be very diverse. If you analyze data from IOR, it's very different from MD test, from spec, from all the different benchmarks that we use. So this is very diverse. Okay. A part of that, we are collecting data from logs of operating system logs, file system logs. We are collecting resource consumption in CSVs, memory consumption, network consumption. We are collecting snaps, logs, and many different types of data that require a process of ETL. ETL in this data will allow us to put all this information, all this data that we are collecting into a very well defined structures to facilitate the exploitation. Okay. Then the results from this data will be deployed into a central repository for efficient access, querying, and reporting. And this will help us to facilitate the historic view of the performance result. Okay, so we will be able not only to analyze the last picture, but also the evolution of the performance of a single environment or different environments across the time, and also correlating the tuning parameters that have been used for that particular environment across the time. Okay. A part of that, we are integrating into this platform mechanisms for produce data mining in order to create descriptive, predictive, and cognitive analytics that will be used for different type of users that we will have in the platform. And the most important thing that I want to highlight today is to provide mechanisms to create, classify, and retrieve performance tuning profiles according to all the data that we are collecting. So we already have all this data, how we are deriving these tuning profiles according to the different variables that we see in the data. Okay, a general overview or a conceptual overview of this performance or data-driven performance approach is like this. We have all the incoming data, that is what I have mentioned, logs, traces, benchmark results, etc. And what we are trying to create here is a parsing and structuring engine that will deposit everything of the useful data, yeah, because we are doing a lot of cleaning, a lot of blending, merging data into a central repository that I will explain how it's composed in further slides. And then this data is going to be available for a processing engine that will be create reporting, that will be create dashboards, and of course will be connected to machine learning APIs for produce insightful models, and also to use this data to create the tuning profiles classification and retrieval according to the description of a particular environment. So the goals that we have with this platform at the very beginning are two. The first one is to create the dashboard and reporting section to produce performance analysis dashboards. And the second one is related to the classification and selection, and could be retrieval of the tuning profiles. The project objectives is to automate the data processing, to change from a perspective of providing the knowledge base on documents to provide the knowledge base on data, as we are currently doing with the knowledge base. In a knowledge base for best practices, we are providing clearly documents that you can make an interpretation for applying this into your own environment. So moving from document to the data, particular data that will give you the exact configuration that you have to use for or based on the characteristics of your environment. We want to see the whole picture, not only the last results obtained for a particular environment, but the historical view of the performance, and also to get much more insights using descriptive, predictive, and cognitive statistics. If we zoom in into this solution, we have the architecture overview. The architecture overview, again, we have all the input data that will be composed of the different sources that I have mentioned before. And here we have what we call the data-driven platform. Okay, the data-driven platform, it is composed initially by the extract, transform, and load ETL module that will take everything, ingesting all this data, all these files into our platform, and in some way transform everything and put it into a scalable data storage. We are talking about a cluster that could be scale out based on the needs for storage, and also we have an scalable data processing engine that we also can scale out based on the characteristics or the needs for processing the data. We are enriching all the processing and all the storing with machine learning and statistics modules and APIs that will help us to apply some algorithms on this data to make something more insightful with the data that we are collecting. And finally, we have interface for cognitive. This is still not implemented. What we are looking in the first phase of this project is to have the scalable data storage, the scalable data processing, and the machine learning and statistics APIs in place. And with these three modules fit the interactive user interface that will be produce reporting, analytics, trends, alerts, custom data views, and analysis. And finally, for the second phase, what we are trying to do is to create an API to let other IBMs or third-party tools get connected to the environment and make useful things with the data that we have already collected. How we are deploying the solution? Well, starting from the back, we have the big data processing. We were using an Spark cluster. Okay, Spark is very convenient for us because it allows to produce inline and offline analysis of the data. So if we have the need for inline analysis, of course, we have some APIs for Spark that can help us. But if we have to mostly do batch processing, okay, Spark is also giving us all the tools for completing the processing of the data as we require. They are connected using some Python APIs to the two databases that are composing the data storage. The data storage is composed by a Cassandra cluster and also by a Mongo cluster. We are dividing in two because while in the Cassandra cluster we are storing the well-defined the data in well-defined structures, let's call it tables. Okay, in the MongoDB cluster, what we are storing is the document itself. So if you are storing a configuration or a tuning profile, the most useful thing is to store it as a single document, because in that single document, you are putting all the parameters and all the values for those parameters that needs to be tuned in a particular environment. Okay, so when you are retrieving this from the MongoDB cluster, you are retrieving everything. Okay, that makes the system very efficient. The same as we're doing with Spark, we are connecting these MongoDB and Cassandra clusters using Python to an application layer where we are deploying all our logic, all our views also in a Django application server for creating the interactive interfaces to our users. Which benefits are we obtaining from this architecture? Well, it's very flexible, it's extensible and efficient, and let us to store, query, and process the performance data. That means if we are acquiring more and more data, we can easily scale the number of nodes for storage and also for processing. We are acquiring this data very constantly in our systems. That means we are running a lot of experiments every week. So we are getting benchmark results, traces, logs, snaps, and everything in a very high amount, on a very high quantity of data. So we have to create an architecture that helps us to grow as the needs of storage and processing also grows. It supports the historical query analysis of view of the results that was one of the objectives of the project, and could be extended not only to the analysis of the performance for the spectrum scale system, but also what we are looking is it could be applied to a different products that we have, and include it into a different levels, not only for the software-defined solutions, but also, for example, at the storage level solutions, we can also include into this platform. Okay, it makes all the data centralized and available for all the users, for all the performance engineers that are working on the field, and can have access directly to the data and the configuration profiles used by other engineers in other parts of the world, and that can extremely help them in order to shorten the times for producing these configurations. Okay, it will also allows custom data analysis to produce deeper insights using, as I mentioned, predictive, descriptive, and cognitive analytics. And the most important thing, use machine learning to enhance the data utilization for the classification and retrieval of configuration and tuning profiles. So now we are going to talk about this machine learning-based configuration profiles repository. The example use of case is selecting the closest tuning configuration according to a system characteristic. So imagine that we are going to a particular data center and we have a system in hands and we want to configure our software-defined storage. So previously in the lab with POCs and also with customers, we are collecting data from different sources. We have data from the description of the overall solution where we have the node, the CPU, the memory, network, storage, disk types, operating systems, versioning, etc. We also have description of the workloads, if it's database, if it's software built, if it's VDI, if it's metadata intensive, the I/O access pattern, resource consumption, etc. And also we have the description of the tuned file system configuration that we have done in the lab and that we have done previously in other environments, okay? And we are linking this description or this configuration with the particular observed performance results. So that means that our configuration or tuning profiles are not going to be just a set of values that are going to be there stored in a database. They are just supported by a set of results that you have obtained previously in similar scenarios. So all this information, architecture, workload, file system configuration, performance data, is what we call the environment profile. So this is introduced every time we produce analysis on a particular system with particular characteristics. Basically, we store all the information related to the characteristics of the hardware, software, workload, and create the environment profile. So now that I have in place a new or enhanced a new system, what I have to do is to look which systems that I have configured and tested previously are similar to the one that I want to configure now. Okay, and for this we are using a machine learning technique called case-based reasoning. We are trying to do baby steps in this. We want to maintain it easier. So what we have think here is if we maintain it closest to what happened in reality, we can handle it better. In this case, how an expert or how a human expert do it, well, it recalls similar experience made in the past from their memory in order to be applied to a new case, okay? So basically, this is what case-based reasoning is doing. So we are retrieving previous cases from a memory or a knowledge base that we have and trying to apply these old cases or the knowledge that we have from old cases to this new case. Probably will we require to revise this old case retrieved and adapted to be used in these new conditions, okay? So using this technique that is part of machine learning and artificial intelligence, we are trying to classify and also to retrieve the tuning configurations. How we are doing? Well, we have the environment profile that has all the data that we are collecting from the different environments that we are testing and we are tuning in some way, okay? And then we are passing it to our platform, our data-driven platform. So we have our module, if you remember, our first module that is ingesting all the data into our platform is the extract, transform, and load. That is the ETL. Okay, the ETL will be enriched in this operation, particularly with the machine learning APIs, and particularly with this domain ontology that will help us to mine what we call the component vector. A component vector, if we want to see it in a very simplistic way, is just a vector with descriptors of the domain, okay? So I will give more details about this ontology, but basically we have a set of terms that are related to the domain and how these terms are related to each other. For example, synonyms, for example, dependencies, for example, which term is more important than other. So we are creating a semantic description of the domain using an ontology. And based on the extract, transform, and load module, and using this ontology, what we are creating first is this vector of components or component vector. So basically it's an index that will contain all the characteristics that are important in the domain that are described in the environment profile. Okay, so now we have this component vector that describes entirely the new environment in which a particular configuration has been applied. And the first thing that the extract, transform, load module does is to store all the data in a very well-defined structures, as we have mentioned, using the Cassandra database. So we will have all the data in tables here to be used for querying, reporting, analysis, etc. Okay, and also we have the entire configuration of the software-defined storage solution is stored as a particular document or object in our document-oriented database that, as I mentioned before, is Mongo. So here I will have all the configurations separated from the results that we are obtaining from that particular configuration. And how we are storing it? Well, we are using this index to store this particular description of the configuration in this database. So it looks something like this, okay? We have an exemplar that basically in the theory of machine learning and case-based reasoning, an exemplar for us is going to be a new case, a new configuration. And this is a very abstract way to represent the ontology, where we have an environment, we will have different type of components in the environment, solutions, workload, network, storage. Okay, there are different type of solutions, there are different types of workloads, networks, storage, etc. So the exemplar is going to have characteristics from the different components of the environment. And once we have created the exemplar, we are, as I mentioned, storing it into document-oriented database, okay? And we are going to use the entire vector, component vector that we have created to work as an index for this particular document that we are storing here. Okay, so in this way, we are classifying the particular tuning profile based on the characteristics of the environment. So we are taking all the characteristics of the environment, using it as a key for storing the configuration that we probably will use later in another scenario, and storing this separately from the data. How it looks implemented? Well, we are using an ontology web language, OWL, to represent the ontology, in which here I am just presenting a snippet of this ontology in which we have the term, for example, InfiniBand network. Okay, this InfiniBand network is a type of or subclass of a computing network, and then we have different ways we can refer to this particular term. For example, InfiniBand could be described as IV network, InfiniBand, Infini-band, and so on. So using the ontology, we can break the ambiguity of describing a particular term in the context of the description of the environment. Okay? So basically here, we are showing how a particular element of this ontology is being described. Okay? Also, we can describe the importance within the domain. For example, if the network is more important than the storage, or the storage is more important than the network, we can start assigning weights. We can start describing a relationship between different elements, not only for synonyms, but also to use terms that are contradictory, etc. So we can do many things. We basically can apply all the semantic to the domain using this language. Okay? And in the database, we have a snippet of the cases insertion in MongoDB, in which we have as an ID the vector of components that we have created. We also have a document reference, okay? And this document reference will create a link between the document that we are storing in Mongo with all the performance data and performance results that we have in our database, okay? So this configuration will be supported by a set of performance results. It's not just the parameters that we are having here with the different values for configuration, okay? So here, this is just a snippet. We can have any parameter that is required in our solution, in our software-defined storage solution. So basically, this is what we use to classify it, and this is how it's being classified and stored in our MongoDB repository. Now, how we are retrieving this information. Now, imagine that we are going to a new place, okay? And we have a different environment in hands, and we want to configure our software-defined storage solution based in the new characteristics of this environment, okay? So the first thing, the user, that could be a human, or could be also a third party or another system that provide a description of the environment in natural language, okay? Provide this description through the user interface. The user interface passes it to the machine learning module that, again, is being aided by this ontology of the domain. It basically is the same ontology that we are using to classify the profiles at the beginning. Well, we are now using it to also create a component vector of the request, okay? So the user provides the description of the new environment through the interface. The interface uses machine learning with the ontology and create this component vector that is what we call the request, okay? And once we have the request created, that is this new component vector, we go to the ontology and retrieve all the exemplars that are there, that at least has one element from the request component vector, and then go to the document. First of going to the document-oriented database, what we are doing is comparing the similarity of the component vector request with the component vectors that we are obtaining from the ontology. And once we have a threshold of these different vectors, we retrieve the ones that is most similar with the request that the user is presenting, or that fulfill a threshold that the user has established. For example, 80%, 70%, 60%, 50% of similarity. But at least what we are looking here is to close the gap between starting from scratch in the configuration of the software-defined storage solution with and help the software, the performance engineer, to do this task. So how we are looking that action here? Well, we have the component vector again, where we have ESS, GL6, genomic, and etc. All the parameters that in some way are describing the new environment that we have in place. Okay, we go directly to the ontology and get all the exemplars that at least has one of the characteristics that we are obtaining in this environment, and then create a rank based on a similarity function of these different environments. So as I mentioned, we can retrieve the one that is most similar or the one that fulfills a particular threshold defined by the user. And when we have defined which exemplars are we retrieving, okay, we go to the document-oriented database, and from there, using these indexes, we are obtaining the particular configuration profiles or the particular tuning profiles that in some way or in some degree are similar to the one that we want to configure now. Okay. And finally, we have the evaluation and adaptation phase, in which, of course, this set of configuration or tuning profiles are given to the performance engineer, okay? But the performance engineer now has to evaluate how these solutions fit to the new case, okay? Could be the case that with the same parameters, although there are some difference in the environment, we are obtaining the expected performance. That can happen, okay? Could happen that we are not obtaining the expected performance, and the software and the performance engineer has to modify in some way the configuration to tune it even more and provide what is expected for the customer. And then once the performance engineer do that, it has to evaluate again all the solution with tests, collecting traces, collecting results, etc., and provide this new profile or case profile to the system. And it's going to be stored as a new case into the general knowledge repository. Okay, so basically at this moment, what we are doing this is manually, still. Once we have retrieved the similar cases, we are passing it to the engineer. The engineer has to apply it into the system, and based on the results that he's collecting, he will decide if he will maintain the configuration or if he is modifying the configuration, adjusting other parameters or tuning some values in the parameters that they has been suggested by the system. And if it's that the case, it has to reinsert this as a new case, as I mentioned at this moment, in a manual way. What benefits are we obtaining here? Well, using a domain ontology as the structure that we're using for classification, it allows us to eliminate what is the terminology ambiguity by using synonyms, by using other type of relationships between the different terms that are composing the domain. For example, I give you IV or InfiniBand could be described as IV, InfiniBand, or InfiniBand. So when engineer goes and describes a new environment, it can just use its own term. Even we can use different languages to explain terminologies. So it's very flexible to explain the domain and all the semantics that the domain involves. Okay, with more evaluated cases, the system develops expertise. That is the same that is happening with human expert. If you start training human experts, the experts start gaining more and more expertise as they are facing new challenge, as they are facing new environments. So we are doing the same, but here we will have the experience or expertise of all our engineers in a single place. So we are expecting to have a very, very strong system. Okay, the tuning profiles here is not just a document that contains the parameters and the values. Here we also have a lot of results and also an analysis that is not only for a particular period of time. We have an analysis that is spread from different periods of time and supporting all these parameters that we are presenting as a best configuration profile. And finally, the proposed architectures allow us the interaction not only with humans, but also can be used by other applications to start thinking about automated configuration processes. Actually, there are other projects at IBM that are trying to generate automatically the values for the configuration parameters and applying this in an automated way into the customer environments. However, they are lacking of an infrastructure or a platform to store all this knowledge that they are creating. So here is where we are just converging as a single solution, where we are just providing this platform for storing, classifying, and also for retrieving all the knowledge that has been generated. And this is something that I have to be clear. We are not providing the values for the configuration parameters. The values for the configuration parameters are being determined by a human expert or by a system, yeah? But what we are providing is a mechanism to store all the knowledge created by these experts, being human or a machine, into a well-defined repository that can help later retrieval of this information in a very efficient way. So we have some successful use cases when case-based reasoning has been used for sharing expertise and for using past cases to resolve new cases. And of course, we have a lot of things to do. First, we are in development. We need to properly evaluate the platform. So far, we have numbers about the precision and recall of our retrieval mechanism. But I think that we need to go beyond that, because what we want to measure is how we are helping the engineers on field to solve real problems. Actually, precision and recall of an algorithm is not giving us that sense. So I think that we need to carefully select the metrics that we are using to evaluate this particular use case of the data-driven platform. We need to explore more similarity functions. So far, we are working with key closest neighbors or nearest neighbors. and also using Euclidean distance, something very simple for creating the similarity. There are a wide range of functions of similarity in the field, so we need to evaluate much more in this particular topic. We need to explore deep learning for the adaptation and revision of the solution phase. So at this moment, as I mentioned, we are doing it manually, but we want to automate this phase too using deep learning. Finally, we would like to take this approach to different environments and start just getting it mature with more and more cases in order to make it more expert, okay? And as I mentioned, we also have the possibility to integrate this knowledge base with other approaches that are looking to find the actual values of the configuration profiles. That's all that I have for this presentation. If you have any question or comments, this is the time. If not, I am letting you my contact details, and from there you can reach me at any time. Thank you.